They promise. So I'm going to try to do something I hope that will be interesting in these two lectures. What I want to do is talk about stars and galaxies and try to teach some of the basic properties of stars and galaxies. For those of you who are astrophysicists, I think all of what I'll cover today ought to be familiar to you, though I'm hoping by doing it this way with just sort of back-of-the-envelope numbers, this will be an interesting approach and a novel way, perhaps, for thinking about it. And for those of you who are particle physicists who've not taken any astrophysics, what I want to do today is give you the basic physics of stars, and in the next lecture talk about the basic physics of galaxies and say what sets those properties. Because after all, as cosmologists, if we're interested in using galaxies to trace large-scale structure or stars to measure distances, to look at properties of dark energy, it's good to have a basic understanding of their properties. And what I want to do is do that in a way that does sort of back-of-the-envelope calculations to show the scaling laws that determine the properties of stars. So if we think about stars, they really are a wonderful system for theoretical physicists because, we joke about assuming a spherical cow, but stars really are, to first approximation and second approximation, pretty spherical. And you can basically characterize a star by its mass. Once I tell you the star's mass, that's most of what you need to know about its properties, determine its properties. There are secondary things that will come in. If stars do rotate, and there's a kind of a perturbative correction you can think of what are the effects of rotation. Stars do have variations in chemical composition. That, again, sort of a perturbative correction. But to leading order, we can think about them as simple spherical systems. And we want to think about a system like this. It's good to work out what are the characteristic timescales. The first time scale to think about is what is the free fall or dynamical time for the system. If I had a star of radius r, mass m, only gravity, this shell would collapse inwards under acceleration. We can work out the characteristic time scale by doing something I'll do throughout this lecture. I'll replace time derivatives by just 1 over t squared. And that gives me that the dynamical time is going to be r cubed over gm to the 1/2 or 1 over root g rho. This dynamical time is going to set the time scale on which deviations from things like hydrostatic equilibrium would show up. And this is a very short time scale. For a neutron star, this time scale is a millisecond. And that's going to be the dynamical time on which things happen. For a star like our sun, the time scale is about 1,000 seconds. The characteristic density in the sun is about the density of this piece of wood here of order of gram per cubic centimeter. When we talk about galaxies, we'll see that the dynamical times are longer, typically of order a couple 100 million years. And when we look at clusters of galaxies, the dynamical time will get comparable to the Hubble time. And then we'll have to worry about initial conditions. I'll come back to this more when we talk about galaxies, but broadly speaking, I think we can think about complex systems and ask the question, are their properties determined by their history, by their initial conditions, or are they determined by equilibrium processes? When we look at the microwave background, we're looking at a system that's determined by initial conditions, and we use linear theory to work out the Green's functions and see how we go from initial conditions to what we observe. The other limit is black holes. The no-hair theorem says you don't care about the history of a black hole. A black hole is characterized by 3 numbers, and since in astrophysical black holes only 2, this charge is neutralized, by mass and angular momentum. Stars are much more like black holes in the sense, because this dynamical time is so short, these systems are in equilibrium and forget their initial conditions. This dynamical time, of course, is the same time scale that arises in cosmology. If we look at the Friedmann equation, again, you see that this is 1 over t squared goes as g rho, and this dynamical time is just another way of talking about, it's equivalent to the Hubble time, or the Hubble time equivalently is a dynamical time. So this is the first time scale we need to think about for stars. The second time scale is the Kelvinhelmholtz time. If I have a star of luminosity L and mass m, the gravitational binding energy, of course, is gm squared over r. And the time it takes to radiate that gravitational energy is the Kelvin-Helmholtz time. And this time scale, it's about 30 million years for the Sun. You can see that this time scale is much longer than the dynamical time. So we can approximate the star as being in equilibrium. But it's a pretty short time scale. This disturbed our colleagues 100 years ago who didn't know about nuclear fusion, because they concluded that the Sun, couldn't be much older than 30 million years old. That's how much energy was available. They were missing physics of nuclear burning. And there was historically a bit of a dispute with some of the geologists who thought the Earth might be older than 30 million years old. This time scale is actually quite relevant for a lot of things in stellar evolution. Those of you who have seen the Star Trek episode, I think, where they send some bomb into the Sun and turn off nuclear reactions in the center, and a few seconds later it turns black, wouldn't work that way. If you turned off all nuclear reactions in the Sun, this is the characteristic time scale on which the Sun would change, right? Takes that long for the energy to diffuse out. This is the time scale on which protostars evolve. Stars start out, they form in molecular clouds of gas. Cloud cores form and collapse gravitationally. And as they collapse, their source of energy is their gravitational energy. And their characteristic evolution time is going to be set on the time scale it takes to radiate that energy. So for protostars, this million-year time scale is the relevant time. Stars, of course, are powered by nuclear energy. If we didn't know any nuclear physics, the longest time we can get a star to shine if we convert all the mass to energy. So I have an Einstein time scale. This would be about 10 to the 13 years for the Sun. If it converted all of its mass into energy, it could shine for that long. The Sun, as a main sequence star, doesn't get all that energy. It only gets to burn hydrogen to helium. In doing so, the Sun liberates about 7 MeV per nucleon. And the Sun does not burn all the hydrogen to helium. On the main sequence, it only converts the material in the core, tens of % of the available fuel. So for the Sun, this efficiency factor is of order, 10 to the minus 3. So this characteristic time scale for nuclear burning it's about 10 to the 10 years for the sun. And the fact that these time scales are so different means we can approximate the star as being in hydrostatic equilibrium, in thermal equilibrium with a constant source of luminosity, and not worry about, unless we're interested in very long timescale evolution, the changes induced by nuclear burning affecting the star. As we'll see, there will be regimes in stars in which we make the star massive enough, these timescales get close, and their evolution gets more complicated. As we'll talk about as we go forward, the sun goes through several nuclear burning stages. The first stage is burning hydrogen to helium. Stars more massive than the sun can burn all the way to iron. In terms of energy available, there's 7 MeV burning through helium. There's only another couple MeV going all the way from helium to iron. So most of the energy available is in hydrogen burning. Once you form the helium nuclei, you've already used up most of, in a sense, the energy content for nuclear burning. Nuclear burning is sort of interesting to think about in terms of what particles are actually involved in nuclear burning. If we look at the rate for nuclear reactions, we integrate the velocity distribution times the cross-section. The velocity distribution is Gaussian for the nucleons in the sun. The cross-section is very strongly velocity dependent, and that's because in order to have nuclear burning, you have to penetrate the potential. And that penetration term dominates the cross-section. So we usually write the cross-section as a nuclear energy dependent part times a term that goes as the charge of the two nucleons. If we're having two nuclei with charge Z1 and Z2, having to overcome the barrier of electrostatic repulsion, which gives rise to the Z squared over R term, this tunneling rate depends on 1 over the velocity. And because of this dependence here, the cross-section is dominated by the most energetic particles. So if you look at this integral, you've got one term coming down like this from the exponential, another term going up like this from the cross-section. So the particles that dominate nuclear fusion are typically about 15 e-folds out in the Maxwell distribution. So it's very rare particles that are responsible for nuclear fusion. Because of this, the nuclear fusion rates are very strongly dependent on temperature. They'll scale as something like temperature to the 15th power. So very small changes in the star's central temperature will have very large changes in the rate. Or equivalently, the star just has to adjust itself a little bit in terms of its density profile to change its temperature significantly. As an aside, this phenomenon of being dominated by the physics way off in the tail of the Maxwellian actually also happens with the microwave background. Kind of the back of the envelope number that you ask, well, when should recombination take place? You would think that recombination ought to take place when the temperature of the universe is about 13.6 eV. In fact, at redshift of 1100, the temperature of the universe, is kind of a third of an eV. And that's because the photons that are ionizing the hydrogen are 40 e-folds out in the tail, And the reason why you get to be so far out in the tail in that case is the photon to baryon ratio is 10 to the 10. So you get to be the 1 photon in 10 to the 10 in the distribution and still keep the system in equilibrium. The fact that we can do this calculation here and get away with using a Maxwellian is, again, the reason this works is because we're in the regime in which all our time scales are long compared to the time scale for nucleon collisions, so that the gas is very much in equilibrium. And the approximation that the distribution function of the nucleons is Maxwellian is an extremely good one in a star. So now let's go to construct a model for a star. Let's begin by writing down the equation of hydrostatic equilibrium. Right, and we can do this because the dynamical time is so short. In order to understand the scalings in the star, what I want to do is compute this in terms of the central properties of the star. A central pressure, P star, mean density, rho star. This pressure gradient we can approximate as P star over R star. And just writing down characteristic numbers, the density is of order m star squared over r star cubed. This says that the central pressure for a star in hydrostatic equilibrium is of order gm star over r cubed. And we can go further in getting the characteristic properties of the star by saying that the star in its center is described by an ideal gas law. That's a reasonable approximation for a star like our Sun. For the very most massive stars, radiation pressure is important. But let's focus on a star like our Sun. The ideal gas law says P equals rho kT over mu, where mu is the mass of a characteristic nucleon. Or mu NP, maybe. There we go. If we do that, we can then solve for the central temperature. And that says the central temperature in the star is equal to the gravitational binding energy. For a star like our Sun, we can plug in numbers, and that gives a characteristic temperature of about 10 to the 7 Kelvin, or of order of keV. That's small compared to the nuclear binding energies, and small compared to the energy it takes to overcome nuclear repulsion, electrostatic repulsion, which is another way of saying that these reactions are taking place in the tail. And the central temperature of the Sun is too low for nuclear reactions to happen quickly, right? That your most nucleons in the Sun will have an enormous number of near collisions before they undergo a nuclear reaction. Second equation I want to use to characterize the Sun is the equation of radiative transfer. So there's energy being transported from the outside of the center of the star to the outside. Energy conservation says things are in equilibrium, so that the temperature gradient goes as the luminosity flowing through the star. Times some constants, where's the density of the star, the conductivity, and the Boltzmann constant here. I can use this to solve for the relationship between luminosity and temperature, writing this as an equation for a characteristic luminosity. You can see that characteristic luminosity, this is T cubed, goes as temperature to the fourth divided by 1 factor of radius here, bringing over the radius squared, dropping off constants. I get that luminosity scales accordingly. And then plugging in for temperature here from this equation above, this says luminosity goes as g to the fourth, mu to the fourth, over kappa. Temperature to the fourth gives me m to the fourth over r to the fourth. Density gives me a factor of r to the fourth over m. Here, canceling all the factors, what I see is that a star's luminosity goes as its mass cubed. So this basic scaling comes from just saying I've got a star in hydrostatic equilibrium and a star in thermal equilibrium. I'm going to get this characteristic scaling. There's a cheat I've done here in that I've ignored the dependence of the conductivity on the density and temperature of the star. And that's a correction I need to put in. If I do that, I get mass going as about 3.5 for stars like our sun, and luminosity going as mass cubed actually is a pretty good approximation for more massive stars. Once I've got this scaling, I can work out that the lifetime of a star, the time it spends on the main sequence, hydrogen burning, will just go as the energy available divided by its luminosity. Since this is scaling as mass cubed, this says that a star's lifetime goes as mass to the minus 2. So short, massive stars, kind of what I think of as like rock stars, they live short, brilliant lives and die early. And this is a pretty rapid scaling. A star like our sun will live of order 10 billion years. A star that's 10 times as massive will live a lifetime that's a hundredth of that. And once we have these scalings, we can see what this implies for a population of stars. Actually, let's see. I'm going to switch to this board. There are many boards. Okay, so if we look at what comes out of star formation, when you form a population of stars from a molecular cloud, what's seen is that the number of stars of a given mass m goes as about m to the minus 2.35. It's saltpeter mass law. This is a good fit to the observations. And this is valid from some minimum mass to some maximum mass. And it rolls over and falls off more sharply at both of those ends. The maximum mass is probably set by the effects of what's called the Eddington limit. if I have a star shining with luminosity L and mass m, that a parcel of gas on the surface of that star is subject to two forces. If I consider the accelerations on a parcel of gas, the gravitational acceleration is, of course, minus gm over r squared. But if the star has luminosity, radiation pressure is going to interact with that gas and cause it to accelerate outwards. The radiation pressure, the acceleration due to radiation on that parcel of gas will go as kappa c over the force of radiation. And for a gas made up of entirely hydrogen, it'll be this becomes sigma t over mp times the force of the radiation flux, luminosity over 4 pi r squared. You'll notice both gravity and radiation scale as 1 over r squared, and that those cancel in radial scaling. So equating the two, there's a maximum luminosity that a system can have. Because if the luminosity exceeds that, radiation pressure will exceed gravity and drive material away. That luminosity is the Eddington luminosity. And equating these two, that's 4 pi gm mpc over sigma t. And that turns out to be about 3.2 times 10 to the 4 solar luminosities for a solar mass star. Yep. Kappa is the conductivity, effectively. Or since I have this scaling as m, this scaling as m cubed, you can see I can equate those two, and that gives a maximum mass. If the star exceeds that maximum mass, which is about of order 100 solar masses, then the luminosity of the star is so large that its radiation pressure drives a wind. And this Eddington luminosity, Eddington limit is sort of a minimal limit. It assumes that the only source of opacity is electron photon scattering. If they're metal lines, which will be a significant source of opacity in massive stars, that is an additional source of photon interaction with the gas parcel, an additional source of radiation of pressure on the parcel, and that will lower the luminosity. If I have all kinds of atomic or molecular lines available, these pressure terms could be even larger. And in fact, mass loss plays an important role in the later stages of stellar evolution. And and as we'll talk about in a few moments, when stars reach the stage of evolution such as the asymptotic giant branch, they lose a lot of mass through radiation pressure on dust grains and molecular lines, accelerating the material outwards and driving gas outwards from the star. The minimum mass of the star is not as well understood. There are a number of effects that set it. When stars form, they're forming in molecular clouds. They're accreting gas from their environment, and their mass continues to grow until something shuts off that accretion. What's going to be essential for shutting that off is some nuclear burning. And so it's thought that the onset of nuclear burning and the resultant winds are probably what set the minimum mass. Given this scaling and our luminosity dependence, we can integrate up this mass function Well, first, just integrating it up for mass, you can see that most of the mass is sitting in the lowest mass stars. When I just integrate up the mass MdM, this is steep enough that the massive stars dominate. But if I'm interested in integrating up the total luminosity of a group of stars, if I plug in, say, mass going to the 3.5 power, and integrate this up, the total luminosity will go as the maximum mass to about the 2.15 power. What the maximum mass of a stellar population is going to depend on its age. If you formed a group of stars at a given time, what happens is you first lose the most massive stars. They have the shortest lives. So the maximum mass gets smaller and smaller with time. Inverting this, you can see the maximum mass goes as the age of the system to the 1/2 power. Plugging that in here, you can see that the luminosity of a stellar population basically falls off as 1/T. So if you form galaxy 10 billion years ago, then it's been getting dimmer over time. And you can also see that the brightness of a galaxy is often going to be dominated by the youngest stellar population. Because if you have a star formation history where you have bursts of star formation, it's the most recent one that will dominate. Guess I want to write down one more scaling relationship before going on. Let me talk about the radius of stars and their effective temperature. I can go back into the equations of stellar evolution and solve for the radius-mass relation. Let me just give it to you. For a star like our Sun, the radius scales as close to the mass. Given this, and the fact that luminosity for a black body goes as radius squared temperature to the 4th, that implies, where this is not now the central temperature, but the surface temperature, this implies that the surface temperature of a star, just plugging this in, goes as mass to the 0.9 power. So that the more massive stars are short-lived and have higher surface temperatures. What we've talked about up to now is purely the hydrogen-burning main sequence phase. This is the first stage in stellar evolution, in which the center of the star burns hydrogen to helium. Eventually, the star exhausts all the hydrogen in its core. That's going to happen on a much longer time scale compared to the equilibrium time scales we've talked about, time scales for our Sun of billions, say 10 billion years. When you've burned that hydrogen to helium, the star then enters what's called the red giant phase and starts burning hydrogen to helium in an envelope surrounding this core. As it does so, it builds up a more and more massive core that's supported only by degeneracy pressure. Once a core is supported by degeneracy pressure, you reach this regime where it doesn't really care what happens when the temperature shoots up. And that makes it unstable to something that's called the helium flash. So as the pressure in the center continues to rise, eventually the center of pressure and temperature become large enough that it becomes possible to burn helium to carbon. Once that process starts, the temperature starts to rise in the core. We saw that the reaction rates are very sensitive to temperature, so they start rising even more rapidly. On the other hand, if your pressure is dominated by degeneracy pressure, the star's central density doesn't care if the temperature goes up, because it's independent of that. So the temperature just continues to rise. There's nothing to relieve that pressure. So the star very quickly undergoes this huge thermonuclear explosion. You're in this regime, actually, where the nuclear burning is happening on a time scale that's actually relatively comparable to the dynamical time. And the star expands and becomes a horizontal branch star. The horizontal branch is sort of the main sequence revisited, except for now we're burning helium to carbon in the core. So we go through the red giant branch, then to the horizontal branch. Eventually you build up a core of carbon, and then start burning helium to carbon in the envelope, and that's going to happen on the asymptotic giant branch. And for a star like our Sun, this is as far as it goes. It burns helium to carbon in the asymptotic giant branch. The extreme radiation pressure drives winds. A star on the asymptotic giant branch actually loses most of its outer hydrogen envelope, leaving behind a carbon white dwarf embedded in first a planetary nebula, but then just left with a cold degenerate core. And that's what our Sun's final fate is. Stars more massive than the Sun are able to burn their way further through the periodic table. Stars whose masses are of order 10 solar masses will burn all the way to iron. And then that iron core will either collapse to a neutron star and produce in a supernova explosion, or will collapse in a supernova explosion to a black hole. And that final fate is going to depend primarily on the mass of the central star. The amount of energy that comes out in these stages, is determined by the energy available. People doing stellar evolution talk about what they call the fuel consumption theorem, that says that the total luminosity emitted during any one of those phases is just equal to the nuclear fuel burnt during those phases. And since there's relatively little fuel available, these phases, in some ways, integrate over the whole lifetime of the system, contribute less of the total luminosity. However, since these stars are so bright, they actually can dominate the luminosity of a system. We can make a rough kind of estimate of just the time scale you spend on each of these stages. So for example, the time scale spent on the horizontal branch compared to the main sequence will just scale as the energy available in burning helium to carbon divided by the luminosity of the horizontal branch over the luminosity of the main sequence divided by the energy available for burning hydrogen to helium. Since stars on the horizontal branch are much more luminous than main sequence stars, their lifetimes are much shorter. So while stars spend, like our Sun will spend 10 billion years on the main sequence, they'll spend tens of millions or to hundreds of millions of years as on horizontal branch stars, or even less in the brighter stages of being red giants or asymptotic giant branch stars. When you're bright, you can't be there for that long. That's just sort of energy conservation. This has been an incredibly hand-waving derivation of star formation, stellar evolution. If you want to see how to do it properly, there's now a wonderful code available that you could download publicly called Mesa. And this is described in a paper by Bill Paxton. Mesa is a very nicely written, stable code. That will let you evolve a star through all these sequences, whether you're looking at low-mass stars, massive stars, or high-mass stars. It's the stellar evolution equivalent of CMB fast, and that you can download things and start playing with them and understanding them. There's a nice story about this code. I met Bill Paxton. Bill is a computer scientist, and after he got his PhD, he started working at Xerox PARC. A few of his friends went off to form a new company they called Adobe. Bill wrote this code called PostScript. Some of you may have heard of it. PostScript did pretty well, and Bill was able to retire. And Bill retired at about 30, and then decided, well, what do I want to do with my life? So he moved to Aspen and went skiing every day for about 4 years. Then his knees gave out. So then decided, later on, that what he really wanted to do was do something fun like astrophysics. So he went and to UC, has a nice place in Santa Barbara, different from graduate student housing in Santa Barbara. And went to Lars Bildston, who's a theorist who does stellar evolution, and said, I want to learn this stuff. And before this code, stellar evolution codes were incredibly buggy. You could run your code for a while. It would work fine as long as you were not on a time scale comparable to the nuclear evolution scale. But things like helium flash would cause your code to collapse, and you'd have to restart the code completely. And Bill said, PostScript is written in a way, it just works. I mean, I've never had the experience of having PostScript fail on me. It's very bug-free. And he wanted to write a computer code, which he did, which is this Mesa code, which is a computer scientist, and a very good one, writing a code under the guidance of an astrophysicist. So it's this incredibly stable code and nice to use. And the lesson is, after you've made your big money and you got to do whatever you want, he became a graduate student and studied physics. And, you guys should appreciate that you have the freedom now, that you're so fortunate that you didn't have to make all that big money first, injure your knees. You could just go right into it. You just don't get the big house in Santa Barbara on the coast while you take your classes, unless you're very lucky. Okay, so let me actually now pull up some slides. Can I have the board? Great. So first, just some slides to back up some of the things I've talked about. This is the scaling for stars in the main sequence stars in the local neighborhood between the star's luminosity and the star's mass. And you can see over a pretty wide range of masses, basically they follow this nice power law behavior with a slope. Kind of the best fit slope to this is about m to the 3.5 here, and then it rolls over. It's a little shallower. It's close to m to the 3 over there. So that our simple back of the envelope estimate of how luminosity scales with mass is actually pretty good. Yeah? I stole this plot. So the most robust masses come from binary systems. So if you've got the best systems to study mass-luminosity relation are eclipsing binary stars. And I don't know if all these points are eclipsing binary stars. But it works if we did that subsample. I wanted to show the rough scaling, so I did the trick of going into Images Google and typing in mass-luminosity relation and pulling down a few plots. This is the, for those of you who haven't prepared lectures yet and want figures, Images Google has made life so much easier. So actually, can we turn down the lights a bit? Just want to get the colors here better. But this is a nice plot to just show pictorially a lot of what we've been talking about. So this is the image of a nearby spiral galaxy. Stars form in spiral arms and then diffuse out of those arms. So if you're looking at spiral arms, you're seeing a stellar population that's much younger. If you're looking between the spiral arms, you're seeing stellar populations that are older. We saw from the basic scaling arguments that young populations are dominated by massive stars that are hot. This color scheme is chosen so that these pinkish regions, this is ultraviolet light in the pink and infrared light in the red. You can see that the spiral arms are very bright in the ultraviolet. That's because the ultraviolet, you're looking only at stars that are very high temperature. The basic spectrum of the star is close to black body. So in an ultraviolet image, you'll see primarily spiral arms. When you look in the infrared, you're seeing older stars, more massive stars, or lower mass stars, and that is a much more uniform emission pattern. One of the challenges for people studying cosmology is because light redshifts, when we look at visible light at distant galaxies, we're seeing light that was emitted in the ultraviolet. So we're primarily tracing young star-forming regions. We're not seeing stars that contain the bulk of the mass in the system. So as we move out in redshift, the flux we see in the visible is an increasingly less reliable tracer of the overall mass of the galaxy, and is much more sensitive to the deep recent star formation history. The other thing that you see in this picture that will be the subject of the last portion of this lecture is dust. There's also these features here arise because a lot of the ultraviolet light emitted from massive stars is absorbed by dust grains and then re-emitted in the mid-infrared and far-infrared. This plot here is how astronomers like to represent much of stellar evolution and stellar populations. This is called the Hertzsprung Russell diagram. What's plotted on this axis here is stellar temperature, and the numbers are a bit hard to read, so let me just go through what we're looking at in temperature. This is 3,000 Kelvin, 6,000, 10,000 Kelvin, 30,000 Kelvin. as we scale in temperature here, along the main sequence, which is this hydrogen burning sequence here, this is a one-dimensional sequence basically in mass, going from low mass stars here, perhaps around 0.3 solar masses, up through a solar mass up to about 10 solar masses here. So this is a sequence in mass, hence temperature. As we're going up in mass, we're going up in luminosity. And this axis here is the luminosity of the star, measured in units of solar luminosity. So here's the luminosity of the sun. 10, 100, 1,000, 10,000, so on. And this is going down to stars that are less luminous than the sun. Stars evolve off the main sequence onto the giant branch. And as red giants, right, they're burning hydrogen into helium in the envelope, then become horizontal branch stars, then evolve up and become supergiants. After losing mass on the supergiant branch, they end up as white dwarfs, which are just supported by degeneracy pressure and no longer undergo nuclear burning. This is an observed HR diagram for a globular cluster. A globular cluster is a gravitationally bound, sort of parsec-size cluster of about 1 million stars. The simple first lecture version on globular clusters is to say they're a single stellar population that formed in a single burst, and that all the stars are coeval. That's what I learned as a graduate student. It's actually not true. One of the interesting surprises is as our studies of globular clusters have improved, we've realized that there's the thickness of this branch is not limited by observational error, but there's actually a range in chemical compositions, and globular clusters probably underwent an extended period of star formation that lasted perhaps of order 100 million years. But for our purposes today, when we're looking at a 10 billion year old or 12 billion year old globular cluster, we're going to say that's an instantaneous burst. So that you initially formed a main sequence that stretched up to here. All the main sequence stars down to here have exhausted all their hydrogen and evolved off the main sequence. What we're seeing here are stars that used to be right here on the main sequence. They've evolved off, going up and are now evolving through helium burning, and then are going to descend down here and become white dwarfs. There are interesting stars here, things that are called blue stragglers. We're seeing stars, some of these stars may be binary stars that are being counted as one object, but some of them are projects of mergers. You have stars in binaries that merge. One of the complexities to this story is most stars are not single stars. Most stars are in binary systems. Most binaries are wide enough that the stars are not interacting, but there are enough binaries with stars close enough that they interact during various stages of stellar evolution, that binary evolution becomes a complicating and enriching part of stellar evolution. And while single star evolution is quite well understood, there, in most parts of the story, binary star evolution is an area of active research. And when you have things like binary stars, white dwarfs merging, that's thought to be one of the mechanisms that powers supernovae. One of the cosmological applications of a system like this is if you believe your theoretical models of stellar evolution, measuring where this turnoff takes place gives you a measure of globular cluster ages. And there's some uncertainty there, but one gets with the current models globular cluster ages that are consistent with our cosmology, which is one of the nice self-consistency tests we have of our basic models. Here's some of the evolutionary tracks for stars of different masses. We talked about a star like our sun goes off the red giant branch and then hits the asymptotic giant branch and then becomes a white dwarf. More massive stars evolve onto the supergiant branch. As 10 solar mass star actually goes back and forth a bunch of times between a red supergiant and a blue supergiant before it explodes. Exactly how these loops are shaped do become sensitive to things like the chemical composition of the star. But this is the basic picture of stellar evolution. Okay, let me lift up I'm going to stop with the slides for a moment. Can I have this raised up again, please? So now we have most of the pieces we need to put together the spectrum of a galaxy, at least in the optical, ultraviolet, and near infrared. We know the number of stars we have of a given mass. We know how they evolve along the main sequence. And people construct synthetic galaxy spectra by combining the outputs of stellar evolution codes like this with grids that tell you how to convert, given a star's luminosity and its temperature, its chemical composition, to estimate what its spectra looks like. And you add together stellar spectrum, which basically look like black bodies with absorption lines, to make galaxy models. The complication in doing this is that starlight is not, much of the starlight doesn't actually get out of the galaxy. As I mentioned earlier, massive stars form in molecular clouds, and massive stars actually spend most of their life in molecular clouds or near them. Molecular clouds contain copious amounts of dust, and dust absorbs starlight and then re-emits it in the far infrared. Dust has been a source of problems for cosmology historically. When 19th century astronomers tried to chart our galaxy, they went on a program of star counts, much like people do galaxy counts today to study the large-scale distribution of matter. What they discovered is we're basically in the center of all the stars around us and thought we were in the center of the universe, effectively. This result was wrong, but wrong for a reason that was a subtle one for them. We actually live about 2/3 the way out in the disk of our galaxy. Our galaxy has a lot of dust in the spiral arms. So when you count stars towards the center, you find that the star counts drop off basically as quickly this way in the visible as this way, because stars here are absorbed by dust. So in optical light, it looks like we're in the center of the universe in star counts. And dust is something that fills not only galaxies, but there's some in intergalactic space. And as we try to use things like supernova for cosmology, kind of a warning is we need to worry at the level of precision we're trying to do to study things like dark energy about dust. We don't want to make the same mistake twice. and ignore dust properties and the effects of dust in our attempts to do cosmology. Well, these dust grains, what are they? Well, it turns out that a significant fraction of all of the carbon, silicon, and other refractory elements in our galaxy are in dust grains. In the outer layers of stars like asymptotic giant branch stars, those expanding envelopes cool, and in those cooling envelopes, dust grains form and then actually grow in the interstellar medium. So much of the products of stellar evolution, carbon, silicon, things like aluminum, are tied up in the dust grains. These dust grains have characteristic size of of order a micron. They range in size, but that's sort of a typical size to keep in mind. What these grains are doing is they're going to be absorbing with optical and UV light and re-emitting in the submillimeter and infrared and into the radio. They're actually emitting at wavelengths that are long compared to their characteristic size, right? And that's what sets that characteristic wavelength of emission is their temperature. They're in thermal equilibrium, and in thermal equilibrium, it turns out, given the rates at which they're radiated, the typical dust grain temperatures are of order 20 Kelvin in a galaxy like our own, to perhaps as large as 40 Kelvin in a galaxy that's undergoing rapid star formation. So with those kinds of temperatures, the peak in their black body curve is of order 100 microns, a scale that's large compared to their characteristic size. And because of that, you work out their emission properties. The cross-section for a grain to absorb or emit long wavelength radiation goes as 1 over lambda squared, right? This is the classic electric dipole problem that you've done in Jackson, where you've got a dipole emitting, and you look at the dipole emission patterns on wavelengths large compared to its size, and it scales as 1 over lambda squared. Because of that scaling, the flux from these dust grains goes as 1 over lambda squared, or nu squared, times the black body emission curve. So it's actually less efficient at emitting long wavelength radiation than a typical black body would be. The black body curve goes as nu squared in the Rayleigh-Jeans tail. So the flux emitted from the dust actually rises pretty sharply, like nu to the 4th. So the starlight that's absorbed by the dust is re-emitted in a modified black body whose peak temperature, peak is of order 20 to 40 Kelvin, corresponding to a peak wavelength of order 100 to 200 microns. And this dust re-emission is quite important because roughly half the luminosity in galaxies comes out not in the optical and near IR, but in this dust peak. So the rough spectrum of a galaxy is basically this modified black body plus the starlight, which is a sum of black bodies from stars of different temperature, with the range covered depending upon the stellar population. So if I have an old stellar population, I'll have a galaxy that's made up mostly of colder, older stars. It'll mostly be this optical infrared bump. If I have a young galaxy, I'll have both the older stars, same bump here, plus the younger stellar population that's hotter and more luminous. Emitting some of its light in the optical and UV, blue and ultraviolet light. And some of this light is absorbed and re-emitted as dust grains. So this is the characteristic spectrum of a young galaxy or one with significant star formation. This is the characteristic spectrum of an old galaxy. Let me show some more slides. Can you lower the screen, please? So here's an observed spectrum. And you can see our basic approximations work pretty well. This is the spectrum of a young galaxy with ongoing star formation. This is the energy per unit frequency as a function of wavelength. This is the optical and infrared emission. The optical part of the spectrum's here, emitted by stars. You'll notice it's basically a sum over black bodies with a few features from absorption lines and stellar atmospheres. This is the dust re-emission. Power law out here with features from the details of the small dust grains. The small dust grains get actually heated to higher temperatures. The dust grains are so small that they're affected by individual photons. So what happens is an individual photon carrying energy of order in EV gets absorbed by a dust grain. It temporarily heats up to maybe 200 Kelvin and then cools down. So the distribution of dust grain temperatures have a non-thermal tail that's responsible for the emission in this region here. But you can see we can get a basic understanding of the galaxy spectrum by thinking of it basically as a sum of stars and reprocessed starlight coming out in dust. Here's the images of a nearby galaxy, M81. It's about 3 megaparsecs away. That's undergoing active star formation. Let's look first at the image in ultraviolet. In the ultraviolet, you're basically seeing primarily where young stars are. Certainly in the outer portions here, these are younger, massive stars tracing out the spiral arms. In the center of the galaxy, we actually have contributions both from young stars and from stars that are on this horizontal branch here, burning helium. You can see that horizontal branch stars, sort of the second main sequence, can evolve fairly far over here and be pretty hot, so that they can also contribute in the ultraviolet. And some of the contribution that you're seeing here in the center is coming from blue horizontal branch stars. As we move to the visible, the spiral arms become less apparent because we're seeing contributions not just from the most massive stars, but over a wider range of stellar masses and hence stellar ages. As we move to the near infrared, the starlight is dominated by the red giant stars. Those are stars that have evolved off the main sequence. And to go back to our globular cluster, it's these stars here that are pretty reddish, that with relatively low temperatures, that are large, you can see these are quite luminous stars, that dominate the light of a galaxy in the near infrared. As we move to longer wavelengths, we're seeing dust emission. So we see the starlight reprocessed by the dust grains and re-emitted here by the larger grains emitting thermally, and the mid-infrared by these small grains heated by spallation. When we start to move to the radio or to the X-ray, we start to see significant non-thermal processes. In the radio, a lot of what you're seeing here is synchrotron emission. The massive stars form supernovae. These supernovae produce shock waves. These shock waves accelerate cosmic rays, relativistic particles, including relativistic electrons. These relativistic electrons emit synchrotron radiation in galactic magnetic fields. So what you're seeing here is these accelerated electrons, and you can see the radio emission traces pretty nicely where the star formation is taking place. And as you look at galaxies, it turns out there's quite a good correlation between their properties in the far infrared, where you're seeing ultraviolet light from young stars re-emitted as dust grain emission, and their properties in the radio, where you're seeing cosmic rays accelerated from shocks associated with supernovae, and these amplitudes correlate nicely. In the X-ray, you're seeing some emission from individual stars, and when we look at more massive galaxies, we're also seeing cooling emission. In the next lecture, I'll talk more about X-rays when we start talking about galaxies and their properties and what sets their characteristic scales. Yes?
Why is the center in the radio, why is it gone dark? So it's kind of just consistent.
So I'm not sure, but I'll give you, there are two possibilities. The synchrotron emission intensity is equal to the magnetic field energy times the cosmic ray energy. So either there's less magnetic field or there's less cosmic rays. My guess is there's less cosmic rays. And that's because there's not much star formation taking place in the centers of the system. So there's not supernova shocks accelerating the cosmic rays. That the acceleration is taking place primarily in the arms. Yeah?
What are the individual sources of radio?
What are the individual sources of radio emission? Those red spots? So there are a couple possibilities. So, this is a particular galaxy. I pulled off the multi-wavelength image on the web to show. And, but one possibility is that a lot of all galaxies, you can approximate a galaxy as having two populations, a disk-like population and a spheroidal population. All galaxies with a spheroidal population or a bulge have black holes in their centers. And the mass of the black hole scales roughly as the mass in that population, the bulge. Why that scaling is seen and whether it's telling us about the black hole affecting the galaxy or the galaxy affecting the black hole is an area of very active research. But we know that galaxies have black holes in their center. These black holes tend to have accretion disks around them because stars are losing mass. That mass loss from stars falls into the center of the galaxy, and some of that accretes onto a black hole and accretion disk. So we may be seeing over here in the center, you often see a radio source associated with the nucleus in the center of the galaxy, associated with black hole in the nucleus. So my guess here is that this may be an active galactic nucleus, and we're seeing radio emission associated with the AGN. I'm not sure what these individual bright spots are. They may be individual supernova remnants associated with bright recent supernovae. That would be my guess. There's often bright spots seen in systems like that. Okay. So the goal of this lecture has been to basically work our way from stars to galaxies, seeing what determines the basic properties of stars from the basic physics, and to try to do it in a way where I've focused on what are the characteristic time scales and processes. In a way, this is an easy lecture to do for stars because we mostly understand stars, certainly have a pretty good understanding of what sets the properties of single stars and single star evolution. What we're going to do next is turn to galaxies. And when we get to galaxies, we have a pretty good understanding at this point of what sets the properties of the dark matter in the galaxies, but less good understanding of what sets the properties of the galaxies as a whole. We understand the individual stars that contribute to the population, but why do spiral galaxies look the way they do? Do galaxies tell us mostly about their initial conditions? Are they to tell us mostly about dynamical processes? Are they more like the microwave background? Or are they more like stars? Is what we'll try to talk about in the lecture on Monday. But I think what I'm going to do is stop here with these galaxy images and our discussion of these different processes. So thanks.